All right, let's jump right in. We're going to tackle an ancient number riddle, one that's been around for centuries. But the key to solving it? Well, that's hiding in a place you'd probably never guess: ancient Greece.
So, what could an old number riddle possibly have to do with something like modern computer security? It sounds kind of random, right? But the connection is actually incredibly direct. The exact same logic you need to solve this ancient puzzle, well, it's also the bedrock for the super complex systems that protect our digital world today. Okay, so here it is. This is the riddle we're up against. On the surface, it looks pretty straightforward, doesn't it? I mean, you could just start guessing, right? Let's see, is it 8? Nope. 13? Still no. You could honestly be here all day doing that. To solve this thing the smart way, we're going to need a special kind of math. So what is this special math? It's something called modular arithmetic. And honestly, if you know how to read a regular analog clock, you've already got the basic idea down. Just think about it, right? If it's 10 o'clock and you add 5 hours, you don't say it's 15 o'clock, you say it's 3 o'clock. The numbers just wrap around once they hit 12. That number they wrap around, the 12, that's what we call the modulus. And this whole system of wrapping around is just perfect for dealing with remainders.
Okay, so with that in mind, let's reframe our riddle. What you're looking at here is the proper mathematical way to write it. That symbol with the 3 lines, it just means congruent to, which is really just a fancy way of saying has the same remainder when you divide. So we're looking for some number, x, that acts like a 2 in a mod 3 world, like a 3 in a mod 5 world, and a 2 in a mod 7 world. It's the exact same problem, just, written in math speak. Now, here's the trick. To actually combine these 3 clues into a single answer, we need a specific tool. See, in normal math, if you have an equation like 5x equals 10, you just divide by 5. Easy. But in clock math, well, division doesn't really work that way. Instead, we have to use this thing called a modular inverse. Think of it like a special kind of opposite, a number that, when you multiply by it, gets you back to 1. And right now, that's the one tool we don't have.
So, that's the big question, isn't it? How in the world do you find this inverse? I mean, for small numbers, you could probably guess and check your way to the answer. But imagine the massive numbers used in modern cryptography. Guessing is, well, it's literally impossible. What we need is a system, a reliable step-by-step method. We need an algorithm. And believe it or not, that algorithm comes from over 2,000 years ago. It's from the legendary Greek mathematician Euclid. Now, he wasn't trying to find modular inverses or anything. He was working on something he saw as much more fundamental. He was trying to find the greatest common divisor, the GCD. You almost certainly ran into this back in math class. It's just the biggest number that divides into 2 other numbers without leaving any remainder. Like for 12 and 18, the GCD is 6. Simple enough. But what if the numbers are huge and messy? How do you find it then? And this is where Euclid was a genius. His solution, which you see here, is just so elegant. It's a simple, foolproof process. You just divide the bigger number by the smaller one. Then you take the remainder and you do it again with the last 2 numbers. You just keep repeating that loop until you can't anymore. It's a guaranteed way to get the right answer every single time. Okay, let's actually try it out with 662 and 414. First, we divide 662 by 414. That goes in once with a remainder of 248. Cool. Now we ignore the 662 and use 414 and 248. Divide 414 by 248. That gives us a remainder of 166. See the pattern? We just keep going using the last 2 numbers, chasing those remainders down and down until we finally hit 0. And that's it. The very last remainder we got before we hit 0 was 2. That means the GCD of 662 and 414 is 2. No complicated factoring, no guessing at all. Just a super clean, efficient algorithm. All right, so that's a pretty cool trip back to ancient Greece. But you're probably thinking, what does any of this have to do with our original riddle? And what about that modular inverse thing we needed? Well, this is the aha moment. This is where it all clicks together. Because it turns out that all those steps we just took to find the GCD, they contain a hidden secret. We didn't just find a single number. We actually uncovered a really deep relationship between our original numbers. So there's this thing called Bezout's theorem, and what it says is that you can always write the GCD of 2 numbers as some combination of those original 2 numbers. The real magic, the secret sauce, is in those 2 little multipliers, s and t.
Okay, get ready for this, because here is the crucial connection. If the GCD of our two numbers happens to be 1, then Bezout's theorem says 1 equals s times a plus t times m. Now let's think about that equation in our clock math world, modulo m. Well, anything times m is going to be a multiple of m, so its remainder is just 0. That whole t times m term just vanishes. And what are we left with? We're left with 1 is congruent to s times a. And that is the exact definition of a modular inverse. That s value, it's the key we've been looking for all along.
Okay, let's bring it all home. We've got our riddle, we've got our 2,000-year-old key from Euclid. It's time to finally solve this thing.
So here's our riddle one more time. 3 separate clues, 3 different clock math worlds. There's a method for combining them called the Chinese remainder theorem, and it gives us the recipe. But the key ingredient in that recipe, the modular inverse, was what we were missing. But now we have the Euclidean algorithm to find it. So the game plan looks something like this. First, we'll multiply all our moduli, the 3, 5, and 7 together. Then, for each of our 3 clues, we'll do some calculations and use our new superpower, the Euclidean algorithm, to find that all-important inverse. Once we have all those pieces, there's a final formula that lets us stitch everything together to get our one final answer. And when you run all the numbers, you get the answer 23. Let's just double check it. 23 divided by 3, that's 7 with 2 left over, perfect. 23 divided by 5, that's 4 with 3 left over. Got it. And 23 divided by 7, that's 3 with 2 left over. It works! It's the one and only solution below 105. Just a beautiful, elegant solution. So you might be thinking, okay, that was a fun puzzle, but why does it matter? Why did we go through all of that? Because it's not really about the puzzle itself. It's about the way of thinking that solved it. That's what literally built our modern world. Think about it. This whole process, using a simple, guaranteed, step-by-step method to solve a problem, that is the absolute heart of every modern algorithm. When your GPS finds the fastest route, or when a search engine ranks web pages, it's doing the exact same thing, breaking a huge, messy problem down into tiny, simple, repeatable steps that a computer can just blaze through. And that's really the big takeaway here. This was never just about a number riddle. It's about a fundamental way of looking at problems. This is what discrete mathematics is all about, finding these hidden patterns and structures in the world and then creating these elegant, powerful recipes, these algorithms to solve problems, whether you're dealing with numbers, networks, or massive amounts of data. It really makes you wonder, doesn't it? A beautiful idea from over 2,000 years ago gave us the key we needed today. So what other brilliant, ancient ideas are out there just hiding in plain sight, waiting for us to find the right modern problem for them to solve?